We now open the LECT2 NPV Excel file and begin by completing the new aircraft product line simulation model. The current slide describes the three input distributions as well as the net present value as the output variable of interest. Okay, so let's switch to the model. I'm going to zoom in on top left corner, and I'm going to start by calculating the revenues based on the demand for a year, 10 units, which is again normally distributed with the average or mean of 10 units plus minus 1, and the distribution seen or appears or is assumed to hold for all 4 years, times the selling price, which is currently 35 million. All the figures are in thousands, but it's going to vary between 30 and 50 million with these probabilities. So most likely it will be at 30 or 40. Okay, perhaps maybe for 45, not as likely the two extreme values. Okay, make sure to fix C10, okay, before executing and copying. Fixed costs, simply assumed to be 15 million per year. Variable costs are given percent of revenue, and the percentage is a value that's uniformly distributed, that will be uniformly distributed between 65% as the best case scenario, 80% as the worst case, currently at 75. Okay, next we're going to fix the depreciation to 10 million per year, simply just like the fixed cost, and then we'll calculate the profit before tax as the difference between revenue and all these costs. The tax is calculated as profit before tax times the tax rate, which is given in G7, and then profit after tax is the difference between profit before tax minus the tax. Okay, because depreciation is not a cash expense, it needs to be added to the profit after tax to get the net cash flow, which under the baseline scenario of 10 units per year is 51.25 million per year. Then the initial outflow is negative 150 million initial investment, which then brings an NPV based on 10% discount rate or required rate of return on the future cash flows, so not the present one, plus the net cash flow or outflow, which is essentially subtracting 150 million to get A, after you get all the decimals out of it, 12.5 million, give or take, okay, which is then going to be reflected in cell C13 as well. Okay, now save this, switch temporarily back to the presentation. Now we're going to implement these distributions in Excel using combination of the rand function, which generates a random number between 0 and 1, and some other Excel functions to get these distributions on selling price, variable cost percentage, and annual demand. So quickly on the rand function, in some kind of, in any cell you can type RAND open close parentheses. Notice that the function doesn't take any input but generates the output such as 0.99, which could represent a high probability of something occurring, or it's simply a number at the high end of the 0-1 interval. If you hit F9, you'll get different numbers, including some of the really low numbers after you hit it long enough, like 8% perhaps, or 4%. Okay, even lower numbers are possible, but you can see that numbers randomly vary between 0 and 1. So these numbers are used to generate these distributions. For example, the discrete, or starting with, I should say, discrete distribution on the price. Okay, so if you look at the cumulative distribution, which actually takes into account these probabilities, it starts with 0, accumulates 10%, then adds 30% to get to 40, adds another 30 to get to 70, 20 to get to 90, and then 1 to get to 100, which I'm not writing here, but you can imagine it being in this blank cell. Okay, like that. So this interval between 0 and 1 is simply chopped up into pieces, some of which are wider like 0 to 0, 0.1 to 0.4 and 0.4 to 0.9 than others like 0 to 0.1. So that random number has a higher chance of falling between zero point 0.1 and zero point 0.4 or zero point 0.4 and zero point 0.7, and therefore representing or generating the 35 or 40 million price, then falling between 0 and zero point 0.1 or zero point 0.9 and 1 and generating the low and high end prices. The way it works, in selling price, you price the fixed value of that lookup that then uses this random generated number, okay, and this table includes the cumulative probabilities as well as the prices, and number two, to get the prices out of the second column to get the results. So every time you hit F9, you're going to get one of these prices. Most of the time you should be getting 35 and 40 because the probability of those two are most likely. Right? See, I'm hitting F9. But sometimes, if you notice, I'm going to get 30 or even 50, although I haven't seen any 50s. Yep, there it is. Okay, as well. Move into the variable cost percentage, which is a uniform distribution between 65 and 80%. It's simply generated by using the min plus open parentheses max minus min then times a random number. The easiest way to sort of intuitively understand this one, if the random number is very small, say 0, then you're going to get I6 or the low end of the interval. If the rand is close to 1, then you're going to get a high end. Okay, but after removing the annoying decimals, you'll see that these numbers randomly sort of vary between 65 and 80%, right? So with low random numbers, you're going to get numbers like 67. With high random numbers, you're going to get numbers like 79. Finally, for this example, we're going to generate the demand with normal distribution with mean of 10 plus minus standard deviation of 1 using norm inverse function, random number for probability, okay, mean for 10 units for mean and 1 for standard deviation. Then what we're going to do next, we're going to fix the references to those two cells because we need to copy this to years 2, 3, and 4, and also we'll put it around the whole thing. Okay, I'm going to put it around the entire function to get the whole number of units. So 10 plus minus 2, right, between 8 and 12 units, sometimes 7, sometimes 13, but very rarely. Okay, so I'm going to hit enter, get 11, copy these guys. I'm going to quickly just get rid of the borders and then reestablish them. That's not important. So if you F9 this, you will sometimes get a 12, sometimes you'll get an 8. Very rarely, the odds of getting a 7 or 13, there's one right here. So this must have been an extremely low random number to get a 7 like that. And if I do this enough, I'll probably get a 13 as well. Perfect. Okay, but none of the other numbers are likely to happen. Okay, so I'm going to save this, switch briefly to the presentation in the next slide and describe what happens next. So next thing I'm going to do is I'm going to reference the output cell from the data table that I'll show you in a minute. Then we'll highlight the table and then run essentially the simulation to create these 100 net present values generated from these three distributions as just described on the previous slide: selling price, variable cost percentage, and annual demand. Then I'm going to summarize the resulting distribution by calculating how many of those NPVs are less than 0 using count if, then the min, max, and average as your basic 3 stats. And I'm going to use a frequency distribution to calculate the distribution table, a frequency table for NPVs. And the whole thing will show sort of the risk profile of the NPV to be in a relatively reasonable 10, 15, sometimes 20% range. So let's do that by scrolling to the right and then referencing that NPV in C13 from the data table here. It's in the middle of the screen, and highlight the entire data table with all 100 trials or simulation runs, and then under where are you, data, motive analysis, data table, column input cell, just click on any random blank cell that will remain blank as well, and L3 is a good example. So this will generate 100 trials, most of which are positive, some of which are negative for the NPV. Then, moving to the right, we will use the COUNTIF function on this range, starting with L6 going to the bottom. The bottom is L105, and count how many are negative. Okay, how many of those are red numbers, and divide by 100 to get a percentage. So even if I had 1,000, 5,000 million trials, it would work the same way. So we get this, 10 to 15% range, although some of the numbers are like 17 and even 19 and 20. I haven't seen, there's a 20. Okay, the min of the same range, L6 through L105, has to be a negative number, otherwise there's really no need for a model if all the NPVs are positive. And then the maximum should be a relatively large positive number, L105, with average obviously in between, right? So the average between L6 through L105 should be somewhere, if I remember correctly, in the 50 million range, 50 to 60, sometimes 40. Okay, the frequencies. Okay, there are three red numbers that are going to represent the risk of NPV being negative. The first one represents those scenarios where the NPV is the loss is really large, more than 50 million. The second one will represent the moderate losses between 25 and 50 million, and the third one, the relatively small losses between 0 and 25 million. The rest of the numbers are positive NPVs. This one is going to be between 0 and 25 million, this one between 25 and 50, and so forth. The way the frequency function works, you highlight all these blank cells, excluding the last one, which is going to fall out at the end, and type equal frequency. The data array is the same L6 through L105 we had in all the other functions. And the bins are all of these except this last one. Okay, then when you close the parentheses, don't hit enter just yet. You have to click with your left hand, Control Shift, and then hit enter, which will then result in all the frequencies being calculated. And then the last frequency of NPVs over 150 million is 100 non-total number scenarios minus the sum of all these scenarios here. Okay, so now if I slide to the right and show you, I'm going to have to zoom in a little bit, show you the NPV distribution, which is this resulting distribution I keep talking about. And if I hit F9, you'll see how the risk profile on the left sort of shows this like 10, 13, 15%, sometimes a little higher, sometimes a little lower range. Okay, so I'm going to switch back to the presentation. Okay, and before I go and continue with the analytic solar platform, I'm going to take a pause.